A driver with mass 50 kilograms drives her car over a hill at a speed of 10 meters per second. That's about 22 miles per hour. The hill has a radius of 15 meters. Calculate her weight in newtons, and how much lighter or heavier does the driver feel as she drives over the hill. So here's a little illustration of what's going on. The driver travels down a straight road and approaches a hill. The hill effectively is a partial circle that has a radius of 15 meters. A asks to calculate her weight in newtons. So we know that her weight, Fg, is equal to mg. So that's going to be equal to 50 times 9.81. And that works out to 491 newtons. So Fg is 491 newtons. Now for question B, what we're going to have to do is employ concepts of circular motion. So we begin with a force diagram, a free body diagram, illustrating the forces acting on the driver. So first of all, we know that we have weight pulling the driver down and the normal force of the car seat pushing up on the driver. Let's just add this semicircle right here to indicate that the center of the circle is down here, which tells us that the positive direction is downwards. So mg is in the downward direction and the normal force is in the upward direction. So now what we do is we write out Newton's second law that summarizes the effect of the force that acts on the driver. Now, the driver is undergoing circular motion, and it takes a centripetal force to make the driver turn into a circle. And the centripetal force is provided by these two forces. So that's equal to Fc. So mg is in the positive direction, and the normal force, Fn, let's change this to Fn. Fn is in the negative direction. These two forces oppose one another. Now they're not equal to one another because she's going over the hill. The difference between these two is what provides Fc. Now we know that MAC is equal to mv squared over r. And we're trying to figure out what Fn is. Fn is equal to mv squared over r. Is that right? That's wrong. Fn is equal to mg minus mv squared over r. Now, what I want to remind you is that what she feels is called her apparent weight. So when you go over a hill like that, what ends up happening is you feel differently because the normal force is not equal to mg, as if you were just sitting there. You're undergoing a change in direction, and that change in direction in this case is provided, the force that causes that to happen is centripetal force. So apparent weight is equal to the normal force acting on our body. That's what we're figuring out here. So what we can do is we plug in the numbers. Fn is equal to 50 times 9.81 minus 50 times 10 squared divided by 15 meters. And Fn works out to 157 newtons. And that means that she feels lighter. Okay? Now the second part of this question is, what is the minimum speed that the driver must move over the hill so that the passenger feels weightless? And you'll notice that the mass of the passenger is not provided, and that suggests that it must cancel out. So let's draw the free body diagram of the passenger. We have weight pulling down on the passenger, and normal force would be pulling up. But in this case, The normal force is equal to 0 because they're weightless. Okay? That means normal force is equal to 0. So we write out Newton's second law. Fc is equal to mac. Here's the hill. This is the positive direction, the center of the circle. So mg is pointing in the positive direction. So we have mg is equal to mv squared over r. Notice the m's cancel. So v is equal to the square root of rg. So that'll be 15 times 9.81. Take the square root of that. And v works out to 12.1 meters per second. Okay, so this would be, or greater. This is the minimum speed. So if the driver goes 12.1 meters per second or faster, the passenger and the driver, of course, because mass doesn't matter, because we've canceled that out, both the passenger and the driver will feel as if they are rising out of their seat at that moment. And the faster you go, the more pronounced that feeling.